tonight, Guy Mansfield. I'll start by mentioning I'm with the Washington State SAR Planning Unit. And that's an all-volunteer group, and we provide SAR planning resources and expertise to assist in extended or complex SAR incidents in Washington State, both in counties and in national parks. We're basically a small private group of volunteers. When we describe ourselves as Washington State SAR Planning Unit, people assume that we're this large cadre of folks with our own helicopters and stuff, but that's not quite the case. I'm going to turn things over to Suzanne, who will briefly introduce Cascadia Search Dogs, and then we'll start with the proceedings.
Hello, everybody, and welcome. I'm Suzanne, and I'm president and founding member of Cascadia Search Dogs. We were established in 2018, and our mission has been to basically support quality training and educational opportunities and to build community amongst canine search and rescue handlers and field support, both locally, regionally, and beyond. So we're really excited about the fact that we have so many countries represented on this call tonight. Several of our members are also on the Washington State SAR Planning Unit. So the idea for this 3-module online course came about, I think it was sometime in the fall last year. And it is free for all of you, as you have discovered. And it's another way we, Cascadia Search Dogs, can support our mission. And again, we're really excited to have such great turnout tonight. So I think we're almost 100 participants or so, and we have others on a wait list. I will share my email in the chat if anybody wants to get a hold of me. And I'll also share the name of our Facebook group, which has a lot of engagement with close to, I think, almost 3,000 SAR canine handlers and field support from throughout the world. And it's called the Canine Search and Rescue Community. So with that, I hope you will enjoy the evening.
All righty, so I'm going to start things off, excuse me, with a couple of polls. This is quasi-experimental, so we'll see if they work. And we just want to find out a little bit about folks' background and how they're involved with canines. And well, okay. So June, I can't get the polls to work.
Hey, let me see if I can get it to go.
Okay, so we may or may not have start things off with polls.
Poll should be showing. People are starting to answer. How long have you been a member of Search and Rescue?
Good. So you'll have to narrate the polls, June.
Okay. Okay, so it looks like we've got a fair amount of people answering. I'll give it just a few more seconds. Okay, I'm going to end the poll. I'm going to share the results. So you can sort of see, it looks like the biggest percentage of people have been with us for 1 to 5 years, and then scattered beyond that. Okay, thank you. And now I'll launch the second poll, which is about your canine partner. Let's see, hopefully I can do that. For some reason, it is not letting me share the second poll. Okay, hold on.
All
Okay,
right.
you should be seeing the second poll. I'll give it just a couple more seconds. Looks like most people have voted. Okay, so it looks like our biggest group is human remains detection, followed by AirSat. So the HRD people will definitely want to be around for the third class.
All right. let's start the remainder of the proceedings then. So whenever anybody gets up in front of a group and starts talking, I always feel it's a really good idea to know something about their background. So without going into lots of detail, I'll just mention that I've got training and background in analytical sciences. I've been very active in SAR for over 10 years, and during that time, I've been a dedicated member of a K9 team. I've taken so many formal SAR training classes that I now probably have forgotten more than I remember. And in recent years, I've been more and more interested in learning and applying search theory to difficult searches. So when I first started searching as part of a K9 team, we simply went and searched where we were told. And we didn't think much about how someone actually planned where to send the search team. So for me, this began to change when I entered into a FEMA tent during the Oso landslide search that some of you will remember. And inside the tent, I saw a map taped to the wall. And on that map, I could see that planners had analyzed slide information to actually predict areas where there was a higher probability of finding slide victims. And for me, I think that started a years-long journey of learning as much as I could about search planning. And that journey ultimately led me to modern search theory. And what I learned was that search theory can provide a better way to guide decisions about where to search, both where to search first and where to search next. And it can also provide a better way for us to understand how effective our searching has been. And so if you stop for a minute and think about the fundamental premise of search and rescue, we're searching because we don't know where the subject is. And on these missions, we operate in a world of uncertainty. And modern search theory is a tool that we can use that applies concepts of probability to allow us to deal with uncertainty in a systematic way. Well, okay, yikes, that sounds pretty scary and intimidating. But before folks start bailing out of our Zoom session, let's consider that we're actually pretty familiar with using at least some probability models. We use a weather probability forecast to decide on our best days of hiking. And we use, some of us use an avalanche probability model to check out the backcountry before we decide whether or not we're going to go backcountry skiing. And when we're out on search assignments, all of us want to deploy our dogs where there's the highest chance of finding what we're looking for. In other words, we want to get the high probability area assigned to us and not the low probability area. So today I'm going to take us through the first of three modules in the series. And right up front, I want to make it clear that the goal of these sessions is not to make all of you search theory experts. The goal is to provide some background context that helps to answer the question that I'm pretty sure all of us have asked at one time or another. Why the heck are they sending us here? So in Module 1, we'll cover concepts that help us answer the question, where should we search? And in the second module, we'll cover concepts that help search planners know how effective searching has been for both humans and canines. And in Module 3, I'll share some thoughts on how to apply search theory concepts to searching for human remains, another area of interest of mine. I do need to start with a caveat. These presentations are rated NIP, that stands for no immediate payoff. Again, the goal is to provide you with insights on how search planners make decisions about where to send your dog team. And this, I think, this will make you a better informed searcher. But if you're dialed into this series seeking tactical secrets about how to better deploy your dog, you're likely to be disappointed. Okay, so let's jump into the first module. I'm going to start with an overview of modern search theory, and then focus on concepts of probability of area and its cousin, probability density. Then we're going to build on these two concepts to see how we can be smarter about prioritizing search assignments. And before continuing, I really need to give credit to those who I've learned from. That would be Hugh Dower, Skip Stoffel and his son Brett, Dr. Don Cooper, Dr. Bob Kester, and others who really have led the teaching of search planning for many years. Those folks are the real experts. Tonight, I'm merely a storyteller. So our session for tonight is going to start with some general observations about modern search theory. And then following that, as I said, I'll introduce the concept of probability of area, which we'll see is really one of the foundational concepts. And then we'll also be illustrating how to think about changes in probability as a function of distance from the initial planning point, such as the point last seen or the last known point. And then we'll end the session by looking at how the concepts of probability of area and probability of density can be extended to make us even smarter about prioritizing search assignments. It's important to start by setting some context for when we actually use search theory. And it's important to realize it's actually used only in pretty special circumstances. The good news for all of us, as well as the subjects we're looking for, is that over 90% of searches are resolved by what is called reflex tasking. Sometimes this is thought of or referred to as the bicycle wheel model. And in this approach, we basically use lost person behavior, historical statistics to define central areas of interest around the last known point, and add to that paying attention to such things as attractants and hazards, and then blend that with what Kester has in his lost person behavior book, a rich description of the characteristics of different categories of subjects. Only a very small percentage of searches require sort of the full application of search theory. And using that is sort of like calling out the National Guard. You only do it when things are getting pretty bad or pretty tough. But this hardcore world, though, is where our state SAR planning unit operates. And also, in my opinion, also includes many evidence searches, which are of particular interest to us in the canine community. So let's take a quick look at an example of why systematic search planning is important. And I can't provide a lot of details here due to confidentiality reasons, but this diagram is based on a real search incident from an unnamed location in an unnamed county, in an unnamed country, on an unnamed planet, and involved a missing 50-year-old with some degree of mental impairment, and who was last seen getting off of a bus in a small town at about this location. There was a large search effort, not guided by the analysis that we're about to see, that did not find the missing subject. One clue was found, a glasses case belonging to the subject. And on top of this, retrospectively, we applied some simple systematic search planning. What we've done is to refer to our lost person behavior statistics and draw our 25% and 50% statistical areas, sometimes called range rings, because we know where the subject was last seen, and we can exploit the fact that his glasses were found at this point. We can make a reasonable guess about a direction of travel based on that and some other investigative work. And then again, based on lost person behavior, we can plot the 25% and 50% dispersion angles. Again, these are the areas in which similar subjects have been found in past incidents. And so with that armchair analysis in hand, we can ask the question, where should we have searched first? And it turns out that this is where the subject was found some months later. And you can see that's in an area pretty well projected, or at least emphasized by a systematic approach to search planning. And so I've said our StateSAR planning unit uses search theory, but we always start with the basics that most of us are familiar with. We gather as much information as possible about the subject and their intentions. We assess their abilities. We try to obtain a last known point or a point last seen. We typically apply intensive terrain analysis, and then also bring in our lost person behavior reference, and then begin to map search regions and develop search scenarios. Okay, well, that was interesting. We just switched to a pre-recorded version temporarily. All right, so we can use search theory to guide decisions about where to assign teams, and importantly, where to assign them first. And I think we're pretty familiar, most of us at least, with what I think of as the universal truths of search and rescue. One, we don't have enough time in our urgent search for a missing child. Two, we don't have enough information. And three, we almost never have enough search resources. And this is particularly true when we have a limited number of search teams. And I'll mention for folks who did not hear anything for that previous slide, is that for some reason PowerPoint switched over to pre-recorded audio, so I had to get off of that. So, all right. So now let's start looking about what search theory is all about. The origins of search theory actually date way back to the 1700s. And it's a mathematical / statistical approach that was described by a fellow named John Bayes. hence the Bayesian method. And the math underpinnings are pretty complex, but the conceptual process is shown here and is pretty easy to understand. So a Bayesian approach provides a way to start with guesses or assumptions, which you then translate into initial statements of beliefs. And then you go out into the world and you do experiments or you obtain objective data. And based on what you find, you cycle back and adjust these initial statements. And then you can repeat this cycle theoretically each time your statement of beliefs is being improved upon. One of the first successful uses of search theory was actually during World War II. It was used in the search for German U-boats in vast ocean areas. And it actually allowed Allied forces to search higher probability areas and in some way contributed to winning the war. And over many years, this search theory concepts, or this Bayesian approach, has been adapted over time to apply to land search operations. And incidentally, the Bayesian model is not just used for search theory, but it's used to analyze a number of different theoretical problems. Here, Bayesian outbreak detection method for influenza-like illness. That's sort of current. All right. So let's see how search theory is actually based on that Bayesian approach. We begin with assumptions and information about what happened and about the subject. We develop incident scenarios and do terrain analysis. We make initial statements, and typically these will be in the form of probability statements about where do we think the subject might be, or probability of area statements that we're going to be looking at in just a couple of minutes. Then we go out into the world and we do our search sorties, and we come back and we calculate probability of detection and how well we covered an area. And then we cycle back and compute how that changed what we think about probability of area, and that influences our planning for the next operational periods. So this is the big picture with sort of a Bayesian background of what the search theory cycle is. So as I've said before, the Bayesian methodology is founded in pretty complex mathematics. Fortunately, for both myself and the rest of us, we don't need to absorb all that math to use search theory. And with some training, we can use the principles of search theory at an operational level. Excuse me. And we can just follow guidelines and procedures that are based on search theory. Okay, so that's good. All right. So search theory can help us answer some important questions. And primarily, it can help us make decisions about where we search first. And later on, if we go through multiple operational periods, it can help guide us to answer the question, where should we search next? And we'll see that the foundation for all of this is the idea of probability, embedded in the concept of probability of area. And this will be the focus of the next several slides. So let's begin, though, by thinking about the basic idea of probability. It's the foundation of all search theory, but can be a concept that's sort of hard to get your head around. So let's consider this simple diagram. You can think, which incidentally I stole from a very interesting book called Math with Bad Drawings. So you can think of probability on a continuum from 0 to 1 or 0 to 100%. And if we look at the left side of the scale here, the probability is 0, and the scientific term for this might be, it just ain't gonna happen. And we progress through, well, probably not, maybe 50-50 chance, probably, and all the way to a probability of 1, it's definitely gonna happen. And so you can see that probability values, or the way we verbalize them, are just spread out on this continuum. And I should add that probability can also be expressed as between 0 and 100%, just like in the weather report. So now let's start diving into the concept of probability of area. Let's imagine that you're looking for a $100 bill, and it might be in region A, and it might be in region B, but you've only got time to search one of these regions. How could probability of area help us decide which region to search? Okay, let's take a look. So in this picture, we've done some analysis and have decided that the probability of area, or POA, in region A is 70%, or there are 70 out of 100 chances for finding that $100 bill in region A. By contrast, only 30 out of 100 chances of finding that $100 are in region B. So based on these probabilities, or these POAs, which region do we want to search? Well, I don't know about you guys, but I'm searching in region A. This concept of probability of area can also be applied to evidence searches, where we're searching for human remains or bones. In fact, in our third training model, we'll do a much more in-depth look at how we think some of these concepts can be applied to looking for human remains, or being smarter at looking for human remains. So what we'll see initially is that we'll be describing probability of area as associated with search regions. Here's region A and region B. But most of us know that individual search areas, or excuse me, individual search regions can be divided up into sub-areas known technically as segments. And there are ways to, in effect, divide the probability of area of the region appropriately into different segments, but we won't have to worry about that tonight. All right, so let's consider a search incident here in which an 8-year-old boy has gone missing from his dad's golf club. He was last seen right about here in the parking lot with his bike. He was riding his bike, but he's disappeared. They can't find him. And so an inexperienced deputy has been assigned to this case. And on a map, he hastily defines 12 different search regions, A through M. And let's take a look at this map and ask a couple of questions here. So first is, if we believe that the boy is somewhere in one of these 12 regions, in other words, the boy is within this perimeter that I'm traversing with my laser pointer, what's going to be the total probability of area of all, if you summed it up for all these 12 regions? Let's think about that for just a second. And it's going to be 100%, because we've stipulated that we believe the boy is somewhere inside this area. All right. So if we now start thinking about, well, where should we start searching first? We can ask ourselves the question, well, which of these regions would have, do we think would have the highest probability of area? And reasonable thinking would lead us to select region G, which contains the area where the boy was last seen, and contains a lot of the 25% or inner high probability lost person behavior ring. And then we might consider, well, okay, what region might have the second highest probability of area? And with some thought, we'd look at the map and we'd say, well, you know, H is really close by to where he was seen and is connected by roads, and he was on a bike. And the same thing for L. So we might assign H and L as second priority search areas. All right. Let's take this same incident and see how we might define areas not with a simple grid, but based on scenarios and terrain, which would be a much smarter and more normal search planning approach. So we can begin by thinking about scenarios. Scenario 1 is that the lost boy has simply wandered off and is somewhere on the golf course grounds. It's hard to see here, but if we looked at an aerial diagram, we could see this red area is basically the golf course grounds. So we think it would make a lot of sense to define this as region A. And if we had another scenario, which might be, well, the boy hopped on his bike and followed roads over towards the river here, because rivers are an attractant for young boys, we might define this riverside forested area as region B. And similarly, there's another area up along the river just north and close by. So we've defined 3 regions here. And then with these better defined regions, we could take the next step and begin assigning probabilities of area. All right, so let's go back to probability of area and consider a slightly more complex example. Here we have not just 2 regions, but we have 4 regions, because on real searches, we usually have 4 search regions, not just 2, right? Right. All right, so let's take a look at this. In this diagram, regions A and B have POAs of 40, and regions C and D have been defined or estimated to have POAs of 10 and 10. Notice that these sum to 100. And again, that reflects the assumption that our subject must be within these boundaries. Now, if we prioritized our search, if we prioritized our searching based on POA alone, we'd rank region A and region B equally. They both have POAs of 40. And that's okay so far, but it'd be nice if there was a way to be even smarter about this, and there is. So now we want to consider the concept of probability density. And this probability density, which is abbreviated as Pden, takes into account not only the POA of an area, but how tightly packed or concentrated with that the units of probability are. So visually here, we can see that the 40 units in region of units, the 40 units of probability in region B are tightly packed, more tightly packed in region A, because region B is half the area. I just saw a good question pop up, which how am I coming up with these probability of area percentages? And the short answer is I'm just making these up for these examples. The longer answer is that for a real search, determining probability of area is a very important and can be somewhat complex exercise, because you want to really be as smart as possible when you do that. And it can be done using objective data out of the lost person behavior text sometimes. More typically, it's done using what's called a proportional consensus process, where you basically get you get together a small number of folks who know the most about this incident, and you show them the regions on the map, and you independently get their estimates, and then you combine those carefully in a specialized mathematical way to get what's called a proportional consensus. That was a good question. Okay. So once we consider probability density here, we can see that region B is a much richer region to search. And so if I'm on a dog team and I want to be on the team that's going to find that missing child, I want to get assigned to region B. All right, so now let's get mathematical here for a minute, not too terribly mathematical. Let's do an exercise where we actually calculate probability density for each of these regions, just to give you an example of how that works. So the formula for probability density is POA divided by area. Okay, let's see if we can do this one at a time. Okay, region A, 40 divided by 40. Okay, that's not too bad. Region B, 40 divided by 20. Well, that's a little bit more complicated, but not too bad. Region C is 10 divided by 40. Oh, might have to get the calculator out for that, but it comes out to be 0.25. And excuse me, region D is 10 over 20. That's not too bad. That comes at 0.5. So you can see mathematically as well that our probability density value here is telling us that if we were going to prioritize these search regions, everything else being equal, we'd prioritize B and then A and then D and then C. Now, in the real world, things get a little bit more complicated than that, but this is the basic principle, or one of the foundational principles. All right, so let's pause for a minute. And a lot of us are familiar with the lost person behavior range rings, as I said, also known as statistical distances. And let's think about the relationship between these distances and probability of area and probability of density. So if we select our subject type, lost child, and we look into Kester's lost person behavior, what we're going to find is that, excuse me, 25% of the subjects have historically been found in the inner area, 50% in the next ring, 75% in the next, and 95% in the outer radius, which we've drawn in this diagram over here. And what I've tried to show with yellow dots are, sort of figuratively find locations for these historical subjects. And there are basically 25 dots in each of these areas. And so we can use that objective data as one way to determine probability of area. I think I mentioned this just a little while ago. And we could say, well, in the inner ring, the POA is 25%, the next is 25%, the next is 25%, and the next is 20%, pretty close. So if we think of POA alone, as we go from area to area to area to area, the POA in each area is the same. But notice what happens when we calculate probability density, because as we go from area to area to area, the size of the area is going up by almost a factor of 10. And the Pden, as we go from the inner area to the outer areas, is dropping dramatically. So many of us have heard the advice, search the 25% ring first thoroughly, and then search it again. And this is one of the reasons, or the main reason for that. Another way of looking at this is a diagram that we actually modified from the guys in Norwegian search and rescue, and we really like this diagram, so we stole it. But here, for example, this is just a reminder that 25% of historical finds have been within this radius, this tiny little pink area in the middle. Therefore, this area has the highest probability density. Therefore, we really want to do a hard target search in this area and search it again. And the same guide gives us a sort of a top level view of how to think about the rings as we go farther and farther away from the last known point or the IPP. One thing that's important, that's an important exception to this model that I'll point out is linear features that may act as travel aids. So these could be roads or trails or ridges or even drainages that can themselves be higher probability areas because they will aid the travel of a subject. That's another thing that we keep in mind when we do our planning. All right, so let's pause now for a review of the concepts we've talked about so far. So we typically begin planning by checking out the local terrain, by defining a search area boundary, and then we characterize and draw search regions on the map, divide that up into search segments, and then for each region, we either estimate or calculate probability of area, and then by dividing by the size of each region, we can calculate probability density. So now, in the next couple of slides, I'm going to show how we extend those concepts by using something called probable success rate, which we'll see is based not just on probability density, but also considers searcher speed and effective sweep width. So let's take a look at this. And we want to go back to thinking about how to prioritize search regions or search segments. So imagine we have two search segments of equal POA and equal probability density. We can ask the question, is there a way to be even smarter about prioritizing where we deploy our canines? And the answer to this is yes. Not only do we want to deploy to the richer areas first, but we can also use this concept called probable success rate, and this which allows us to consider two factors that influence the efficiency of search teams, and that is how fast can they travel and what is their sweep width, how far side to side can they detect things. So to help us think about probable success rate, because this is a little bit of a complex idea, one way is to imagine that as search teams sweep through their assigned areas, they're actually gobbling up units of probability as they move through their search area. So as shown in this highly technical diagram here, it could be useful to visualize your search team as Pac-Man, as I said, gobbling up units of probability as you go through an area. And probable success rate is dependent upon three things. How dense is the probability in the area? And as I said before, how fast can your little Pac-Man team move? And the width of the swath that they cover as they move. And that's dependent upon the term technically called sweep width, which itself is a little bit complicated. So let's look at that in a little bit more detail on the next slide. Excuse me. So when searchers move through an area, one of two things happens. either they find the subject or the probability that the subject is in that area is reduced. So in this slide, you can think about all these little yellow dots as either findable objects or perhaps units of probability. As a team traverses through an area, they will sweep up these units of probability and sweep out a path. Notice though that this is not a clean sweep, and some of these units of probability are left behind. And this is a subtle but important point in the concept of sweep width, and it's the way we build in the assumption that all searchers are imperfect. Now, I know that most of us think our dogs are perfect, but you get the idea here. So now I've simplified this concept a little bit, but the basic outline of this definition is correct here. So to summarize, sweep width is a measure of side-to-side detection width of a searcher, whether human or canine or UAV or whatever. It's a concept that acknowledges that the sweep is not going to be clean. You're going to be leaving some units or possibilities of finding the subject behind. It can be used to quantify how much probability is swept out during a searcher path. Again, whether that's a human searcher or a canine. And fortunately, at least for humans, it can be reasonably estimated using a simple field exercise. And we'll come back and talk about sweep width for canines, I think in the next session, because that's a more lengthy conversation. But let's go back to probable success rate. So let's see how it's used. Let's see how sweep width is used to both conceptualize and calculate probable success rate. Once we know or have estimated a team sweep width, team speed, and probability density, we can go ahead and calculate PSR. And I should stop here because I realize I've left out some important context. Typically, this idea of probable success rate is used by planners before we send folks out into the field. We're calculating in advance how efficient they're going to be in terms of chomping through the probability out there. So it's done before the search, and it helps guide our prioritization of search segments. All right. And again, so the key concept is we're forecasting in advance how many units of probability are going to be gobbled up by the search team per unit time. Let's look at a couple of specific examples. So in this example, we've got two search segments of equal size and of equal probability density. But in segment 2, the terrain is more wide open, and therefore our estimated sweep width, again, the side-to-side range at which things can be detected is broader. So if we have the same team of the same size and the same talent moving at the same speed, you can see that the team moving through segment 2 is going to sweep up more units of probability per unit time. And therefore, the PSR for segment 2 is going to be higher, and we would want to apply search resources to this area first. Let's look at another example. So here we have, again, two search segments of the same size, and the search teams in each segment are able to travel at the same speed, and they're going to have the same sweep width. But if we look over here at segment 2, the probability density is higher. So again, even though the teams are going to be moving at the same speed and having the same sweep width, the team moving through segment 2 is going to be sweeping up more units of probability per unit time. The way this might look back in the command trailer is something like this. We're going to have a spreadsheet where for each search segment, we've got the ID and the segment area and the POA, and we've calculated the Pden. We estimated a sweep width for the team, and we estimated a team speed, and we're going to get a list of PSR values for each segment, and again, use that as a guide to prioritizing search segments. Now, we actually use this approach on an evidence search in Eastern Washington. Actually, it was a search for a missing person. And what we did was we drew all our regions and segments, we calculated PSR, and we provided that information as a visual to the incident commander and color-coded the segments with, red had relatively high values of PSR, orange, medium high, green was sort of medium to low, and gray was pretty low values of PSR. And this was one of a couple of factors, excuse me, used to make decisions about where to deploy teams first. All right, so let's wrap up today's session with a quick review. So we introduced the concept of probability of area, which is either an estimated or perhaps a calculated number that tells us how likely is it that we're going to be looking, that what we're going to be looking for or who we're going to be looking for is inside a particular area. Then we looked at its cousin concept, probability density, which tells us how densely packed or how thick the probability is in a particular area. And we saw how that could be extended to this concept called probable success rate, or PSR, which is an estimate of how many units of probability are going to be swept up per unit time by a search team. And that would allow us to plan the most efficient use of search resources. And by efficient, I'll pause there and I'll say, what that means is overall in the search effort, we want to be consuming or sweeping up as many units of probability per unit time as we can. All right, and then in the next module, which I think is a week from tonight, we'll be introducing the concept called probability of detection and show the concepts that it's built on and how probability of detection is used to quantify how much probability has actually been searched out of an area. And then that quantification can be used as the basis for deciding where to search next if we have a search that goes into multiple operational periods. So that's the end of the formal presentation for tonight. And I'll stop now for questions. I thank everybody for attending and being patient. And Gene, I can see questions as they come up, so I will try to address them, okay? So another really good question, how are we estimating a team's speed by average speed or knowledge of the specific team? This could be both. The easiest way is just to assume an average speed. We did this just last week. Our unit was supporting actually 2 simultaneous searches for missing hikers above the snow line down at Mount Rainier. We actually went through the process of calculating PSR, probable success rate, and we thought about the terrain, and a number of us on the planning unit who were familiar with Mount Rainier. And our thinking was something like this. Well, they're searching above the snow line. In many areas, it's forested and steep. I'm guessing the teams are going to be moving about 1 mile an hour, and we just plug that in as an average speed. We did a similar quick estimation of sweep width and said, you know, bad conditions, I'm guessing their sweep width is no more than 20 feet. And we simply plug that into 6 meters. Okay. Now you can get much more specific and you get better results. You could actually check each team and you could say, okay, how fast do you guys think you're going to be moving based on your past performance? And as I mentioned, you can actually get a pretty good empirical measure of sweep width by doing what's called an A-rod exercise, having each team do that once they get to their search area. So we have a good question from Yvette. How does search management decide which areas to assign K9 teams versus ground searchers? There are probably a number of reasons. We will assign K9 teams where we think that the K9's nose has a better chance of detecting a subject than human ground searchers. And so this is one of the reasons why we on K9 teams get sent into these terrible, nasty drainages. Ground searchers just can't see or penetrate very well, but you know, the dog's noses can. You know, I remember one search years ago where we had one of our K9s at the bottom of this huge briar patch that you just couldn't get into, and the dog was showing clear interest in that briar patch, and sure enough, just a little bit later, that's where the subject was found. There's a question, how do you factor in geography and how much impact on calculations? So let's see. So terrain is extremely important, and I'll try to address that. So let's first start thinking about probability of area and search scenarios. So these are the important concepts at the very beginning of our planning. So we're gonna, and I'm thinking of an example where we have a missing hiker in the wilderness, but this applies to other types of incidents. So we're gonna look at the point last seen, or where we last expected the hiker to be. Actually, so I'm thinking of a real incident that we analyzed in the Sierra Nevadas. It was an elderly gentleman who had hiked into a lake in the Sierra Nevadas to go fishing. He had sent in an I'm okay signal on his spot beacon on Saturday night. And his plan on Sunday was to hike back to his car, which involved, he was familiar with the area, but hiking back to his car involved hiking back on one of 2 cross-country routes to get him back to the trail. And so in our analysis of scenarios and area probabilities, we spent a lot of time looking at the terrain. We identified the 2 passes that he might have taken as cross-country routes. And we also identified what terrain features would be barriers to travel and what terrain features would be travel facilitators. And then when we drew regions, we would subjectively be thinking, well, you know, it's very doubtful that he got over the Palisade Range to the other side. So we might draw a search region on the other side, but we're going to assign a very low POA to that. And so 2 comments here. This class goes along perfect with the MLSO course. Thank you. I've taken that course, and it's taught typically, well, mine was taught by Skip and Brett Stoffel. MLSO is Managing Land Search Operations. There used to be both an advanced and a basic. I think they might have combined it into one now, but it's a good course. Anybody interested in search planning should try to take that course in some form or another. So another question, excuse me. Doesn't temperature, air, wind, ground play an intrinsic part in this as well as terrain? So yes, and as we know, particularly it's important for planning a canine search. And so, and I think that's what you're thinking of, Deborah, but I'll mention 2 sides to the story. So one is sometimes in trying to come up with a scenario for what happened to the subject, air, temperature, and wind direction can play an important role. So for example, if we knew the person was on an exposed snowfield, that the wind at the time he got lost was blowing from, let's say, the west, that the person was likely disoriented in fog, then we'd be thinking, you know, it would be natural for that subject to wander off toward the east more than the west. Okay, so that's an example of thinking about the effect of the wind on a human subject. And thinking about the effect of wind on the effectiveness of a canine search, I mostly think of that in tactical terms. So you know, the handler gets assigned a search area, and they will, either approaching or once they get to that area, they will take those factors into account and decide which side to approach from, or which direction to grid from, or what to expose their dog to first. The statistical search planners, the search theory guys, won't be thinking down at that level, even though it's critical when you get down to the level of operations in the field. Let's see, we have a question from Keith. How do you factor in trailing canine versus air scent canine into your searches? And does time last seen come into play? So 2 questions there. Again, this will go back to, and I think this would be typically a decision made by the ops chief. Do I want trailing canines versus air scent canines? So if, for example, I have a decent scent article or a decent starting place, such as a vehicle that might provide a scent so that I could take advantage of the specialized training of trailing canines, that's something the ops chief is going to want to do. If I don't, or if I have, like I said earlier, sort of larger areas where we want to send canines, then that's more of an assignment for air scent canines. I'm going to think back again just to last week on our search of Mount Rainier. This was a hiker who was last seen on a trail system, probably about 4,000 to 5,000 feet in altitude. We knew about where he had last been seen on the trail by another hiker, but we didn't have a scent article. and it was terrain that would be difficult for a trailing team to move in, I believe. But what the park was able to get was 2 air-sent canine teams who could in fact navigate some pretty tricky terrain. They ended up doing like a 10-mile hiking loop, and I'm guessing that the upper 5 miles of that was crossing snowfields. And so again, the idea is we wanted to take advantage of the air-sent canine potentially being able to detect scent coming from a broad area, up drainages, up valleys there. Okay. So let's pause for a second, see if we have any more questions. Am I using trailing in the same way as tracking? Yes, I am, and I hope that's the correct way to think about that. Basically, I'm thinking of a dog especially trained when given a scent article or a scent starting place to follow that scent on the ground specifically. So questions, are we going to have recordings of these available? We don't have any plans to do that, but it's something that we've started to think about. Oh, well, whoops, my organizer is way ahead of me here. Link to recording will be sent out to everybody tomorrow. Well, that's amazing. Okay, good. Okay, I'll wait just a couple minutes and see if anybody's brave enough to send out another question. Can we share the recording with the rest of the team? No, we put secret listening devices in the recording so that we can detect that and charge you extra money. I'm just kidding. You're welcome to share the recording with your teams at home. Just don't sell them on the internet for money, please. Okay.